All right, hey team, I'm Anthony Nocentino. This is load testing storage performance for SQL Server. I'm a senior principal field solution architect at Pure Storage. It's a really long title to say, especially when your name has like 17 syllables in it. I'm on the internet a lot. I blog pretty frequently. This isn't a vendor session, but I'm going to take a lot of the learnings that I've had working on high performance database systems and apply and kind of share how we build POCs for our customers. And again, also built on a lot of experience that I've had just as a consultant. We have sponsors. They're awesome. Say thank you, shake their hands, visit their booths, which they recently just closed, so you can't really do that anymore. But they'll probably be at the party tonight or the event. We're going to talk a bunch about understanding your hardware's capabilities, especially when I was a consultant. You buy a thing, right? A switch, an array, a server, whatever it is, HBA, and it has a performance profile associated with it. And if you can't hit that performance profile, you're wasting money, right? Or more importantly, you have like untapped capacity in your platform. And so really it's when we're going to spend a lot of time talking about hardware and hardware capabilities. Then we're going to talk about load testing strategies, right? I've seen very many POCs that were just not great architecturally. And then people are like, hey, your storage stinks. And I'm like, you just started up 10,000 threads at the same time. Like that kind of stuff you see. Or like you have folks that'll be like, they'll run a load test with a VM with 2 vCPUs in it. And they're trying to run it against like the highest performing storage device on the planet. And you're like, wow, I can't imagine why you're not making the array work hard. So we'll talk a lot about what we're going to look for there. We'll also talk about a lot about interpreting performance data, because where you measure matters, right? In the sense that when you look at the IO stack, there's lots of things involved to take an IO from memory and flush it all the way down to a disk drive, right? Or an SSD or whatever it is that you're storing on. And so let's get into kind of the hardware capabilities that we want to talk about. So you need to know what's possible with your gear, right? If you buy a 64 gigabit HBA, you want to get 64 gigabits out of it, right? You don't want to plug it into a 16 gigabit switch and be like, huh, that stinks, right? Because you're leaving 400% of the capacity on the table. And so we're going to look at this across a couple dimensions today in terms of physical systems, virtual machines, and also cloud. But what I do want to call out today is we're going to be like laser focused on storage testing, right? And because basically we're talking about database systems, it's as fast as your database can move, right? How the latency profile is how fast transactions can commit. And the read profile or the throughput profile is how fast you can read stuff off a disk, right? And so that really drives how fast you can move your database forward. But what we really want to focus on, like when I'm building actual POC plans for customers, and even when I was a consultant, you want to focus higher up in the stack, right? So this is kind of like a disclaimer. Nobody cares about latency and throughput. That's like a checkbox that you move on and you focus on the bigger picture, right? So when we do like customer POCs, we'll look at things like, hey, tell me something about your business that's important, right? Is there a stored procedure that runs? Is there a business process that runs that you need to go faster? Tell me about that thing. And if that thing's faster, then it provides value to your business. But of course, like the plumbing still matters. Like we did a POC for a customer when I first got hired, and they had a stored procedure that they would run every week that would roll up a report to the leadership to make business decisions about their platform. We made that stored procedure 40 times faster, right? So it went from hours to minutes, which is a massive value to the business because they're getting access to the thing that they want more quickly. So that's the stuff that we really want to be focused on in a POC. But today we're going to be laser focused on storage, right? Cool. So when we look at where SQL Server stores data, right, that's going to be on disks, in files, that can be inside a server via SCSI or NVMe, or outside the server, right, remote storage across the SAN over Fibre Channel, iSCSI, or NVMe over Fabrics. One of the things that we are seeing as an industry trend is a shift, or not a shift away from Fibre Channel, but kind of Ethernet showing up as a first-class citizen in the sense that its bandwidth capacities are far blowing past what Fibre Channel can bring to the party anymore. Right, we're looking at 32 and 64 gigabits. That's the top end of Fibre Channel. Like I get laughed out of a room if I talk about 100 gigabit Ethernet now. We have 400. I've seen roadmap slides for 1.6 terabytes a second for throughput for Ethernet, right? Like think about the velocity that you can move data there. And so we are seeing a lot of our customers in the industry in general absorbing Ethernet again as a storage media, because also the simplicity associated with it not having a completely separate network. But people think like, hey, Ethernet stinks because I have all this converged stuff. Well, right, and Fibre Channel is better because I have point-to-point connections. Well, of course, if you build a separate dedicated network for storage, it's going to perform better than a converged system that's running traffic for users in storage. So you really think about your storage architecture or your network architecture when you have converged Ethernet. So it's not what one is good or the bad, or gooder or better than the other one. It's just easier to shoot yourself in the foot in a converged Ethernet way. So we're going to spend a lot of time talking about how I/O flows through a system, right? We obviously, like, writes are going to go down into storage and reads are going to come back out across database files and log files. And so that's kind of the core thing that we're going to talk about. Is a perfect pun when I say core thing, and we're going to shift to talking about CPUs, right? So when I'm going to devise or build a load test, people think things like they'll grab some old hardware, they'll create a VM with 2 vCPUs in it. The core thing that really drives storage performance, especially in the context of SQL Server, is the clock rate of the CPU that's driving the I/O, right? Because that's quite literally how fast the bits and the bytes can move through the system, how fast I can pull something off of a drive, or how fast I can write it down, because the clock rate of the CPU is what's going to drive that I/O. So when I was a consultant and I'd build SQL servers for customers, I'm like, hey, how big's your budget? They're like, this big. And I'm like, cool, let's get the highest clock rate and the least number of cores, and then scale that for number of processors for your system, right? Because when SQL Server dispatches I/O, a single I/O reader or writer thread is just a single I/O reader or writer thread. It parallelizes the I/O at a higher level in the stack with worker threads, not on individual threads. So those individual threads are only going to go as fast as, how fast? The clock rate of the CPU, right? Cool. So it's super important to understand that. I got lots of fun stories I can tell you over drinks about how I've read manuals over the years and have slid them across the table and said, read page 146, right? This is how fast this system should be. So like when you're talking to the network folks and they're like, hey, it's as good as it gets. Everything's configured fine. And you have to, like, you peel back the curtain and you read the manual for their switch. And they're like, hey, shouldn't I be getting 400 gigabit through this? I'm like, oh yeah, I didn't realize that. All right, so you have to get to that point because the burden's on us to prove that the system's going to be functioning properly. And so go ahead and grab the manuals and make sure that you understand that the performance profile of the thing that you bought, switch, HBA, server, array, you're actually able to hit those capacities because that's going to be the target that you're going to shoot for in a load test, right? Cool. So we're going to spend a bunch of time talking about the hosts today, the interconnects, and also the storage. Cool. So when we look at physical servers, right, some people still put hard drives in servers, much to my chagrin because I work at Pure Storage. But the idea here is you're not going to get any faster, right? Because the interconnect between the CPU and the memory bus is going to be basically PCI, right? And so you can't go faster than that, and it's measured in microseconds. When you're talking about how those are interconnected with the system, you have this concept of PCI Express, which has multiple lanes and generations, right? So we're on PCI 5 now. I forget that I think 32 is the maximum number of lanes. Each lane contributes an amount of throughput to the system. And so we want to make sure that there's not a mismatch there when we put drives in a system, that we're kind of building that in a non-blocking way. My internet just went out of my house. I'm sure I'm going to get a phone call from the family soon. Yeah, so there's also NVMe, which gives you the ability to have parallel queues out to drives. When you compare that to like SATA and SCSI, which were serial queues out to drives. And I've seen some, the only way you can classify it for performance numbers, I've seen some bananas performance numbers with local drives inside of a server over NVMe. On Windows. One of the things I do want to bring up is this concept of NUMA. When you start building multi-socket, multi-NUMA node SQL Server systems, say that real fast, you still have to worry about the locality of memory in really high-end systems. I very rarely see this. I've only seen this twice in the wild where I've had to go to the point where we're laying data files on particular volumes attached to particular HBAs, and more data volumes over here to a dedicated HBA. And then we'll make sure that the worker threads are associated with those files are allocated in a way that we have memory locality throughout the thing. Probably most people don't need that level of performance tuning, but a friend of mine, Thomas Grosher, does, and he's got a whole YouTube video at 8KB from about 2 years ago where he drives you through an architecture of a system that has to function like that. So I won't go too far into that today, but check that out if you want to go deeper in detail on that. I think what we see next, or more frequently than that, is kind of remote storage. The idea is I have a SAN or some sort of external storage that's connected to a server over HBA or NIC. I already talked about fiber channel and Ethernet and the performance profile associated with that. And that's what you're going to get in the storage I/O path here. So if it's 400 gig Ethernet, that's going to be how much stuff I can blow out of that server into that particular storage array. So then again, the NIC and the HBA will have some sort of performance profile in terms of which slots they should go to into a server. And then we'll have some sort of throughput associated with that on the interconnect to the system. So maybe it's 2 by 32, right? We're also going to have multi-padding and things like that, not only for performance and capacity reasons, but availability, okay? And then also the other side of the fence is the SAN that's going to be attached to the network is going to have some sort of connectivity. So that might have a higher number of ports associated with the total throughput that is the performance capacity of that kind of box, right? Cool. Questions or comments, team? Good? Cool. Yeah? All right. So at Pure, I would say we've done some surveying in public. We did this on a webinar once. We asked about 1,500 people, where do you run your SQL servers? Physical boxes in the cloud, VMs, things like that. And 89% of the respondents said they run their SQL servers on Windows on VMware. That's a pretty crazy number, right? To have that number of people, although that number is probably changing for some reason lately. Why do you think that is? Okay. So when we have a VM, you have virtual disks that are allocated, that are consumed inside the virtual machine, that then run on top of some physical hardware, which has some sort of physical interconnect to the remote storage. And one of the key things, especially in VMware, is making sure that your VM config is configured to best practices. I've seen many a times where I walk into a customer site, whether I was consulting or now, and they have 12 virtual disks attached to a single LSI adapter, right? Which is like quite opposite of what you want from a performance standpoint. And so we're not going to go too deep into the best practices for VMware configs, but know that there's a particular configuration you need for SQL Server or for high throughput database workloads with multiple paravirtual SCSI adapters, multiple virtual disks, and balancing your I/O across those. One of the things that we forget about when we're doing like high-end load testing is making sure that we don't have noisy neighbors contributing to the problem, right? If we're trying to measure the performance of a platform, the last thing I want to have is a production workload weasel its way into the environment and skew the results that we're looking at. And we see that frequently as well. For the hypervisor itself talking out to remote storage, same considerations as the last one, right? We need to make sure that we're laying the plumbing out properly for the things that we want to do in the platform. And I have a whole YouTube video here on virtual machine configuration and best practices, but that's a longer conversation to have. In the cloud, we want to understand, again, what we're paying for, right? If I buy a VM SKU, it's going to have a number of cores, it's going to have a number of IOPS associated with, and throughput limits associated with the SKU or the model, I guess for lack of a better term, of the VM that I'm consuming, right? It's going to have limits for local storage, remote storage, and it's also going to have individual disk limits in terms of IOPS and throughput. And so, again, for local and remote. And so we see often, especially when I was consulting, I'd have a customer that have one giant hard drive associated with the entire database attached to a VM that had not enough cores to even drive enough workload into that. And so when we build a virtual machine in the cloud, we want to make sure that we don't put an artificial bottleneck into the system. Maybe the VM SKU only has so many IOPS and I don't have enough disks to even get close to what that VM is providing to me. And similarly, network throughput. We're seeing things like eSAN pop up and other external storage in the cloud. We have a product as well where the storage is over the front end network because it's just iSCSI out to that storage platform. And that goes out the shared network throughput of the VM. And so you have to take that into consideration if you're using that type of storage in the cloud. Not necessarily managed disk, but eSAN or other external iSCSI attached solutions. Cool. iChart, forgive me for that. Actually, that doesn't look too bad. Come across pretty good, yeah? What do you think, Mike? Good? Yeah? Yeah. Anyway, when you're looking at a VM type, this is the EDBV5 SKU, and what you're going to get is a performance profile associated with the number of cores in the system. And there's temporary storage inside the system, which is great for things like TempDB on SQL Server. But as you can see, as it goes, more cores gives you more capacity and also gives you more throughput in terms of how you can consume that storage in IOPS or megabytes. And obviously, going back, we also have a maximum number of disks. Each disk contributes some amount of IOPS and throughput to the system. How much? Well, that depends on the disk topology that you're using. Looking at things like premium SSD, there we can see there's a performance profile associated with that, an upper boundary. See at the bottom there we have 8,000 megabytes and 260,000 IOPS. Similarly, Ultra and Premium SSD V2, again, that's the performance profile that they bring to the party in terms of IOPS and throughput. The idea I want you to walk away with here is when you're sizing a VM, these are, if you're devising a load test, these are the upper limits that you're going to shoot for, right? If I'm paying for 400,000 IOPS on a 112 core VM that costs my business $112,000 a month or $120,000 a month, I want to make sure that I'm hitting that number, right? I actually deployed the 96 in my Azure account for like 7 minutes, right? Because I didn't want to, but I wanted to get the whole thing deployed and do a quick test. And yeah, that lights a lot of money on fire. I think that one's close to $90,000 a month, right? And if you want to have HA, You need 2, right? Cool. Yeah, so just kind of going across, you can see like just the performance profile of the 96 core one. So, and this is the NVMe edition. There's also a SCSI version of that as well. Cool. Questions or comments about hardware? Cool. You're like, man, after lunch. Now we're going to talk about queuing theory. It's going to get even better. All right, so when we're looking at a system, right? SQL Server dispatches I/O. The worker threads get kicked up. They talk to the database files. They talk to the SQL Server, which talks to the potentially the hypervisor or the underlying OS. There's a storage interconnect and there's storage. And I have a bunch of ways that I can measure this performance, right? I have DMVs inside of SQL Server, right? Which is a method to get performance data out of SQL itself. I have this thing called wait stats, which is whenever SQL does a thing and it's got to wait for the resource and it times that for me. And then disk latency, potentially network latency across the storage interconnect, and then the actual storage latency itself. And so again, writes go down, reads go up. And these are all the points that we have to understand where we can measure, but it's also transition points for I/O where I could saturate a resource, right? And so if each one of these layers presents the potential to inject latency and queuing. What I mean by queuing is I'm driving too much work faster than a layer can transact that for me, right? And I have to go all the way down the stack and all the way back up the stack on a read to be able to measure that latency and also protect against the risk of queuing in an environment. And so that's what we're going to go to, is we're going to test a system, we're going to drive workload until we can get to a point where a system is queuing. And what do we do then? We'll talk about that. All right. So load testing strategies and tools. All right, let's get into some fun stuff. There's this thing called Little's Law in queuing theory. It says that doesn't even have anything to do with storage in particular, but it's applied to storage. When I have a system, any system, there's 3 characteristics of behavior for the system itself when I have to move things through a system, right? How much stuff do I have to move is the number one thing, like operations per second, or generally throughput. How long it takes for the thing to move through the system. In our conversation here, it's going to be block I/O. That's going to be queue time, right? How much time it's spent waiting to get access to the thing that's going to transact the thing for me. And then there's inventory. How much stuff has to be done? I kicked up a bunch of work and have to get through the system based on how much it can do it and how long it takes to do it. The YouTube link on the bottom here, I kid you not, is a 2.5-hour deep dive on queuing theory applied to Disney World. Right? Because the same exact concept apply, right? I have a line of people that rush to a thing. The ride can only process so many things at a point in time. It takes this long to get on the ride and off the ride, and all that applies. So if you really want to get nerdy, check that out. So fun stuff there. We can assert influence on a system by changing one of these characteristics, right? You know, I talked about making sure we don't have bottlenecks. Well, that's the number one thing that we can do, right? We can influence the system by changing how much stuff can be transacted, right? If I have a 32 gig NIC or HBA that's a bottleneck, I can go to 64, or I can go to 100 gig Ethernet. But on the other side of the fence, I have a storage controller that's out of CPU capacity, which is really what's going to drive latency, or how fast I can transact the I/O. I might have to get a better storage controller, right? Or a better disk drive that can transact things faster, right? And so we can use this theory to kind of analyze the system that we want to work with and influence by changing one of those metrics, right? And so when I first got hired at Pure, someone told me this, and I was like, that's crazy. I never thought about it that way. But IOPS times how big the IOP is how much stuff I'm moving, which is called throughput, which is a very practical way of viewing it. For some reason, it was like a light bulb moment for me. And then I also have IOPS times how fast I can conduct the transaction. Latency is really going to drive average queue depth, right? So that's going to be the upper boundary there. So with these 2 metrics, what we can do is apply this to, you weren't expecting to see like a good chart like this today, were you? Here we are. This is pretty much what is the goal for devising a good load test, right? Your system is going to have some sort of characteristic latency, right? How fast it can conduct a transaction. This system here, 0.3 milliseconds, right? Or 300 microseconds. And that's going to be consistent, right? It's the dashed line is how fast it should be. But as I add load to the system, I increase the IOPS. What happens is we start to observe latency, right? We've all seen this in systems, right? You're like, oh, it's good, it's good, it's good. And oh my God, it's bad. What happened? That's what happened here. We get to some point where we saturate the platform, and that's really the target that we want to go after when we're devising a load test. People ask me all the time, well, how should I configure HammerDB to learn a load test? Depends. You have to find that point, right? Because at that point is when you have to decide, is the system's performance good enough or bad enough for your business? right? Is it okay that your array latency creeps up to 3 milliseconds? It might be, right? It might not be. So some folks need it to still be 0.3 milliseconds. So they won't drive load to that point. They'll drive loads to a lower point. Then we also get to this point where it's saturated. Like I've had customers that'll come to me and they'll be like, hey, I ran a load test with 100 worker threads and we're seeing latency. I'm like, yes. When you put 100 concurrent threads on 64 cores driving out a workload, some of them are gonna have to wait, right? Because we're hitting a bottleneck somewhere in the system. Most likely if I'm doing 100 threads and 64 cores, I'm probably saturating a physical connection somewhere along the way because I'm driving that amount of IO, I'm gonna basically bottleneck somewhere in the platform. So just when you observe load tests, the knee or that inflection point is what you're shooting for. How much that is really depends on the infrastructure that you have. Cool. What do you do when you hit the saturation point, right? I can change two things. I can do less stuff, well, three things. I can do less stuff, right? Reduce IOPS, or I can increase the throughput of the system, buy bigger pipes, or I can buy a bigger processor on a storage controller that can process things faster, right? You have to apply Little's Law to how do I change one of those parameters to drive more workload. Cool. Questions, comments? Mike? No? Good? All right, cool. So the other thing that I talk a lot with folks about is synthetic or real workloads. What should you test with? What should you test with? Synthetic workloads? Raise your hand. Nobody. Cool. Real workloads? Mike doesn't test with any workloads. He's my coworker, by the way. Yeah, obviously, like as engineers, we might not have access to real workloads, right? Because we're not running the frontline apps. But we really, like I talked about earlier, you want to find something that you can get your hands onto that really is measurable to the business. But in the end, when we're doing this type of testing, it's probably going to be a synthetic workload. And so when we're doing synthetic testing, we're going to look at things like throughput and latency. In real workloads, we're going to talk about things like transactions per second, that critical stored procedure that I told you about in the beginning, or other key performance indicators that are important to the business. One of the things that I had the luxury of doing is I worked for a large American toy manufacturer, and I had to help them through Black Friday every year, right? And one of the more challenging things we had to do was make sure that we could handle the surge that the system had on Friday and Monday associated with holiday shopping, right? They made toys, people buy toys for their family at Christmas. And one of the goals was when someone hit add to cart and checkout, right? It was like 3 to 5 seconds tops under like the highest load, because what happens if someone hits checkout and it takes a minute and a half? You don't check out, you close the tab and go somewhere else, right? And so that's a very key performance indicator for that customer. What they want is when they inserted data, they had to get to that point. And we really did some fine tuning to get it to their database. Actually had what's called last page insert was the final bottleneck that they had, which is a real hard problem to solve after that. It's a big fun. Yeah, it's a checkout. Cool. All right, so what are we testing for? Again, it's kind of thinking wider load testing strategies. OLTP versus OLAP, right? Transaction processing or analytical processing. So transaction processing latency is king, right? How fast can I flush my transaction log into disk, right? We talked about 0.3 milliseconds a bit ago. We're seeing trends towards 100 microseconds or 0.1 microseconds, even into the high 80s now, which is like a bananas amount of latency when you think about how fast you can transact in I/O. Generally speaking, analytic systems are going to be reading lots of data and transposing it, so the throughput's going to be kind of the key player there. One of the things that I do have to, a myth that I have to debunk frequently in our customer base, and even just in general in the SQL Server community, is that SQL Server doesn't perform 8K IOs. Neither it doesn't even perform 64K IOs. It just performs the IO size that it needs to transact the operation that it needs to do, right? And so you can ask your SQL Server what its average read or write size is. And then when you go devise a load test, that's what you're probably going to test for, right? So we'll talk to customers, or I'll talk to customers and say, hey, what's your average read and write size into your database? You can get that out of SQL Server. I have a blog post on that. And then you devise a load test for that. So you'll generally see like an OLTP system land around mid-30s for writes. And probably mid-teens for writes, mid-30s for reads. And an OLTP system, OLAP system, you'll see probably 100 to 200 for reads and about 60 to high 50s for writes. That's just the way that SQL Server writes those IOs out. And so if we're devising a synthetic load test, those are the numbers that we're going to go after, right? And so you get those from your SQL Server. Log flushes can be any size from 512 bytes up to 60K, which can be interesting, can lead to some interesting performance characteristics in 4K disks. We'll talk about that over beers tonight. SQL Server can also do what's called read ahead which gets you up to 512K. One of the things that we also have to talk a lot about is a bigger I/O, surprisingly. Right? If I read 512K, it takes longer than a smaller I/O. Make sense? Yeah? Yeah. Cool. And backups, anywhere from 1 to 4 megs. You can tune it down too. Backups becomes one of my favorite ways to actually test load on a SQL Server, because I can really dial granularly the size of an I/O down to 64K up to 20 megs now inside of if you're backing up to Blob or S3. So you can get some pretty cool testing out of that, and also some concurrency. I'll show you a backup test in a few minutes. There's the blog post that I promised you. Cool. Let's see. I'm going to jump ahead. No, I'm going to do this one, then we'll jump ahead, because the time management is a problem today. So DiskSpd's still a thing. I was at a Microsoft event about a month ago, and their engineering team showed me a test in DiskSpd, which made me happy, because I know DiskSpd still. It makes me happy that it's still relevant. And they're still contributing to the project. It's open source now, and you're starting to see some pretty cool functionality come out of that. HammerDB is still relevant as well. We're seeing it a lot in the field in our customer base to validate storage. And there's a project from a friend of mine, Gianluca Sartori, called Workload Tools. This is a really cool tool where you can quite literally run an extended event on a SQL server, and it'll relay the workload to another SQL server. Yeah, it's like all the promises that Replay Trace had, or DEA, but actually works, right? And then SQL Server itself. So these are kind of like the suite of tools that I use, except DEA, when I work with devising load tests. So DiskSpd, 100% synthetic. HammerDB is certainly synthetic, but it runs TPCC or OLTP workloads, or TPCH, or OLAP workloads, so you can kind of get a fixed, controlled test. Workload Tools can run your actual workload. DEA can run your actual workload, but it's also deprecated. And in SQL Server's both, right? I can run stored procedures and code that I know, or I can drive tests like I'm going to show you in a little bit. This DiskSpd really just focuses on the storage elements. When you bring something like HammerDB to the party, you have to worry about the configuration of SQL Server. And so you're really kind of shifting away from just the raw storage testing to a wider story about how well a SQL Server is performing. So you have to make sure that you take that into account from a design standpoint. Yeah, play back your workload, an actual workload, but also synthetic. Like I said, I use backups as a fantastic way for storage testing in SQL Server. Cool. So this system that we're going to work with today, I have a physical server running against a storage array. We have an HBA. This is really old, right? Really, really old. PCI 3 in an 8-lane slot, an 8-lane card that should get me about 7.8 gigs a second. I have the servers attached to the storage network with 2x16 HBAs, and then the array itself is 6x16. And so again, how fast or how should I design a load test? Well, I know the characteristic latency of this platform is 0.3 milliseconds. And based off that interconnect of the HBA into the storage array, I should get 4 gigabytes, big B, per second out of the system, right? So that's what I'm shooting for. Not great, it's like 1997 numbers, but it's what I have, okay? So let's get into some tests. So leveraging DiskSpd, I have all the kind of the parameters walked through here. I'm using a larger block size. I'm going to do about a 1-minute test just for show. This is a super important flag, -SWU, which disables the file system cache and any hardware caches associated with the system. -L measures latency, and I'm going to start off with 1 outstanding I/O and 1 thread, right? Because remember, that single clock rate thing is the thing that I want to go after, and then I'm going to scale the test based on that, right? So it's going to run. I should have ran the test and not talked while you guys have to sit here and watch this load test run for the next minute. My apologies. No, just kidding. I edited the video, so it shouldn't take an actual minute. Or did it? Does it? No, it does. All right, so I fast forwarded a little bit. Going through the output, we see a bunch of stuff that's interesting. It's kind of spitting out the characteristics of the test. The duration was a minute. We have a data file on a drive. You can see software cache disabled, write-through cache disabled. We're performing a sequential read test of 128K. You can see the physical topology of the system. It's a 2-socket system with 48 cores. Higher performance plan, 1000% important. If you're of a certain age, you know what the turbo button is on a computer, right? Quite literally, the power plan is like the turbo button from the old days, because if you have a balanced power plan on, when C states kick in, it's going to lower the clock rate on the system, right, to save power. What's that mean to us? Lower throughput. Eventually it'll come back up, but I don't want to have that skew the results of my test, right, or the results of my real workload in production. So let's go ahead and run this test here. We'll kick that off. You can see the CPU utilization is really low. All the cores in the system, it was only a single threaded test, and I did this well. I drove 400 megs of I/O at 3,277 IOPS. So that's single threaded. So now I have like as fast as a single thread can move in my system. So now it's time to figure out where the knee is in the platform, right? I'm gonna drive the test to that point. So let's go ahead and kick up the next test. Jump ahead here. So now I'm gonna jump it from one outstanding I/O to 10 threads. So I kick up 10 threads. So you'd expect, what, 400 and something times 10, close to which would be the upper boundary of the platform, right? About 4 gigs. Let's see what we get as a result here. So that finishes. Let's go back up. The only thing that stinks about recorded demos is you forget like how slow you were back in the day. So each thread contributes a little less throughput this time. It's about 230 and it caps out about 2,300. So there's some more meat on the bone here in terms of throughput because I'm shooting for 4 gigabytes per second and I'm getting about 2.3 gigabytes per second in the system. So I'm gonna go ahead. One of the things I probably could have changed in this test is added more outstanding IOs right there, but I'm gonna keep going after threads and just kind of have that be the knob that I'm gonna turn. Let's go ahead and jump forward on the system. Now I'm gonna go to 20. Oh, I should point out, the latency of the first test was about 0.3, the single threaded test. The latency of the second test with the 10 threads landed at 0.5. So we're starting to see it creep up a little bit, right? Cool. All right, so let's run the 20 thread test now. The 0.5 was the 10 thread test. So the 20 thread test is running, and we're gonna see a different latency profile here in a second. Fast forward a little bit. There we go. So 0.799 or almost 8. So quite double the latency profile of the overall system. So now we're starting to get to a saturation point, and the throughput that we have is 3126, about 3 gigs and change, right? But we're starting to creep up the curve again. So what's that tell you? Something somewhere is starting to slow down, right? Now let's double it and just give it a ridiculous amount of workload and see how it reacts. So I have 40 threads. And so this is basically how I devise a load test, is I kind of just massage threads until I get to the saturation point. Now we know I should get 4 gigs, and I'm about a gigabyte per second short on this platform. So it tells you like something smells funny in this test, right? The 40 thread test, 1.59 milliseconds. All of a sudden we're back to like 2006 performance profile, right? Because I'm sliding up that curve, and I've gone well past what I would expect the platform to provide. And this is what I want you to look at. This is on one of our storage devices. And what we do on our system is we can measure how much time in I/O is spent on the wire. Like, so quite literally, once it leaves the block driver, it hits the HBA on a Windows box, and by the time it gets received by the controller, that can be measured. And so what you see is that light blue is that amount of time. And so we see that it's called sand time in our platform. In other platforms, they have a different, it's classified as a different metric. But what we saw as we slid up the curve there in that 40 thread test, that we saw about a millisecond and a half of latency. That's almost entirely in the network. Something is wrong between the HBA itself and the array. So this has nothing to do with how fast the server performs. It has nothing to do with how fast the array can perform. We've literally saturated something along the way, right? This particular system, I'll tell you, I'll let the cat out of the bag, is I intentionally have the HBA in the wrong slot. And it says limiting the HBA by the number of lanes it has access to, because I want to be able to show like this phenomena that can occur. So quite literally, if I just move this over one slot and I go to an actual 8-lane slot, I solve this problem, right? But the load test showed there was a configuration anomaly because I expected a certain performance profile and I didn't get it. And so we can see each iteration of that test, the 1 thread test, the 10 thread test, the 20 thread test, and then finally the 40 thread test is where we see that kind of fall down. All right, 10 minutes. We're gonna do this part. So Performance metrics. When we're looking at a system, we've discussed that the important metrics that we care about are latency, throughput, and IOPS, right? How long it takes to do the thing, which basically means like transaction log stuff. Like when I hit checkout, it's a function of latency, right? Because I'm gonna flush an IO out to the system to be able to go and conduct that transaction. If I can't process things fast enough, right, I'm gonna get queuing out of the platform, which we saw. The amount of throughput is the amount of data moved. It's generally gonna be a function of the storage interconnect and also the type of storage used. And IOPS is a funny number because as you learn, SQL Server conducts all varying sizes of IOs. So if someone comes to you and says, my platform needs 100,000 million gazillion IOPS, your reply is, what's your IO size, right? Because that's gonna define how fast the thing actually needs to be, right? Because it's really the size of the IOP is application dependent. I was working with a DB2 instance that was flushing IOs out at 4 megabytes. That's a big IO, right? Cool. So when we're looking at SQL Server, excuse me, we have drives that hold the data that are connected to the system in some way, right? Over a storage network or inside of a box and interconnect. And I have some database files that work is gonna get conducted at. So if I spin up a worker thread that drives an IO, at this point in time, when that worker thread puts the IO down the stack and makes the request of SQL OS to push an IO down, it starts counting then, right? So the DMVs and await stats count at that point in time. The operating system starts counting once the IO hits the actual block driver in the IO stack, right? So I push that down, now I have an IO and I'm timing there. That's gonna be average disk seconds per transfer or latency, right? Disk bytes per second is how much the throughput, so these are the performance counters inside of Windows. Disk transfers per second is IOPS. And now if I do something inside a SQL Server like select star from and just let a query go wild and this happens and I have a bunch of worker threads kick up, each one of those worker threads is accounting for their time when they start, right? So who's had the phenomenon where their DBAs are like, my latency is 200 milliseconds and you're looking at the storage control and you're like, it's 0.3 microseconds, right? You ever have that disparity happen? That's exactly why, because they're looking at it at that layer, right? And so that's what's literally happened is they're probably having queuing somewhere along the way. And so when those IOs actually hit the block driver inside of Windows, they'll hit a queue, and that's gonna give you the average disk queue length. And that's when you start to pay attention as storage pros. You're like, hey, all right, well, you're saturating up there, I'm seeing saturation here, then we can start to figure out where that latency is being injected. And then average bytes per transfer would be the average IO size, right? Which becomes a metric that you're probably interested in when you're figuring out the capacity of a system. Cool. So let's go ahead, I'm gonna jump right into a demo because I wanna show you that phenomena occur. And so the last two slides, if you wanna give a quick look, which is like where you can collect performance data, but I've seen a lot of heads nodding today, so you probably know where performance data comes from. I'm gonna jump to, we're good. I'm gonna do all the demos, 8 minutes. All right, so the workload that I have here, so if you look, and it's kind of small, backup database, Stack Overflow to disk equals null. So what this is gonna do is gonna kick up a single reader thread and read the bytes off of the drive and just throw them out. I'm not gonna write them anywhere, right? So it's a fantastic way to emulate a single threaded read, right? How fast I can move a single threaded read through the system, right? Cool, so let's go ahead and kick that off. So right now, I'm getting about 20 IOs queued, but is that bad? Not really, because even though there's 20 IOs queued, I'm still servicing them below the characteristic latency of the system. So queuing here isn't bad because I'm getting a good latency profile through the system. I'm just driving a lot of work. Then average disk transfers per second. So just about 0.4 milliseconds or 400 microseconds for the disk latency itself. Cool. So we'll jump ahead and show you what SQL Server sees. Who would have thought backups were so exciting, right? I love taking backups. Sorry, right there. So the backup ran just shy of 3 gigabytes per second. Okay, so 29.54. Really bad at math. Now I'm gonna kick up a backup with 4 reader threads, right? So I have 4 reader threads and 4 writer threads, but it's gonna write to null. So it's throwing them out. Now I'm seeing a little bit more latency, about 0.7 microseconds, a little bit more queuing, about double, but I'm still servicing a workload well. Let's see, it'll be to get, like I said, queuing's about 50, but we're gonna go back and we're gonna see is when that finishes, I'll fast forward a little bit. It finished in 3,063 megabytes per second. So what I gained, I added 4 threads and I gained about 100 megabytes per second. Does that sound like a good bargain? No, right? I didn't bring a lot more to the party. And you might be thinking, well, the single threaded test that you did earlier, you got 400 megabytes per second. That's because the I/O size is a lot larger here. It's about 1 meg, where the I/O size in the first test was 128K, all right? So now I know I hit a bottleneck at around just shy of 3 bytes per second, same bottleneck that we saw a few minutes ago, but now I'm observing that at the application layer. Cool, and we can see it visibly here. So the single thread test, I got about 1.5 milliseconds of latency in the network, and we already know, I let the cat out of the bag on the secret and on what's going on here. We can see that, and then I run the 4-threaded test, I'm definitely bottleneck, and I really don't get much more in terms of throughput. The bottom chart here is the throughput. You saw I only gained about 100 megabytes per second. Cool. Let's go ahead and do the final demo, which if you're the astute observer, you can see will take 5 minutes, and we have 4 minutes left. So there's a community stored procedure run by a gentleman named Brent Ozar called SB Blitz First. It's fantastic for gathering performance data. And so what we're going to do is I'm going to drop clean buffers and run a select star query from a giant table. This table is about 100 gigabytes, right? So it's the Stack Overflow database. It's all the posts associated with that. Now, if you look here, now we're looking at something bad, right? So I'm getting about 5,000 IOs queued. So 506 is the value here, but the scaling factor is 10. So 5,000 queued IOs, not great. Disk latency, where is disk latency? Disk transfers per second is gonna be, seconds per transfer. That's about 20 milliseconds, right? Modern storage array, bottleneck, 20 milliseconds. What's going on there? Let's go ahead and jump back and we'll look at this inside a SQL Server. So when that stored procedure finishes, when that query finishes, Brent's stored procedure is going to report to us some interesting values. And so when I talked about where you measure matters, right, that big I/O thing with queued IOs, what you see here is I got page I/O latch, which is me dispatching an I/O down the I/O stack. That's the SQL Server wait type for that. And so it took 28 milliseconds for the underlying disk subsystem to service that I/O. Because remember, all the threads are stacked up and weighted, and they're all in line to get out to the underlying disk. And then the same thing at the bottom here, you'll see the individual data files themselves from DM Virtual File Stats is showing me a different story, right? It's aggregating all the stalls of all the times it had to wait for the saturated disk subsystem. So again, 235 milliseconds. And there we see 43 milliseconds of time wasted waiting on the network, because all those threads dispatched I/O and they were all queued and waiting to get access out to the drive. And so this particular system is purposefully, like, again, misconfigured. Let me go back here. The max degree of parallelism, or the max number of threads SQL Server is allowed to dispatch when it creates a query plan on a system is unbounded. So I have 48 cores of SQL Server queuing up to throw I/O down a completely bottlenecked and saturated system. Right, so that's why we're seeing these crazy numbers from the different ways that we can measure. So if I go and I'm gonna jump to the end. So that was the 48 core plan. I'm gonna jump to the 2 core plan here in a second. So the 2 core plan, which I restrict the degree of parallelism of the query to 2 instead of 48, we already know I can get a pretty good amount of throughput out of a single read thread from a backup. When this finishes, we'll see a much more better behavior out of the system with the characteristic latencies that we'd expect. Let's go ahead and let that finish. So the 2 core plan. We'll go back to Brent's stored procedure here. We'll go to the bottom. The last time we looked at this, the page latch I/O, which is SQL Server waiting for I/O, was the top wait. It's now the 5th wait. It's at about 0.8 milliseconds. And then the average drive stall is 4. And if we looked at the perfmon counter, we'd see it be about 0.4 milliseconds as well. So again, we're in the universe of where we want things to be, and we're getting no SAN time. We're getting the actual characteristic latency out of the storage network at this point in time. So when you have DBAs that come to you and are like, hey, I'm getting 200 milliseconds out of a query, now you kind of know like there's a deeper conversation than just how fast is the interconnect to the platform. Because in this case, the workload itself was accounting for all of the weights because it spun up 48 cores, and all of them basically had to get in line to get access to a completely bottlenecked storage subsystem. Cool. Let's go back here. Yeah, so the question is like, how do you design a load test? I don't know, depends, right? But now you kind of understand the theory about what you're going for, right? You have, single threaded throughput, we have the characteristic latency of the platform, and you see that large inflection point, which you highlighted a couple times with disk speed, and we saw it with the query at the end there. That's how we have to really define like what's good and what's bad. So clearly I should fly to Santa Clara and I move the HBA one slot over and my system's 25% faster, right? Or I just need to buy something that was made like in this decade, right? Cool. Yeah, so just to review, this is the biggest thing I think I want you to walk away with is understanding like what the capacity of the platform is, load testing tools and strategies. There's no magic button to driving a load test or building or devising a load test. My partner in crime at work, Andrew Prusky, and I, we took HammerDB. We're really excited about this. We took HammerDB and we put it in a container and parameterized load tests so that very easily you don't have to worry about the configuration of HammerDB. You just say, I want a database that's this big and run a test with this many threads. And then it's up to you to figure out where the curve is, right, in the platform. And so that's available on my GitHub repo if you want to check that out. And we talked a lot about like where you measure matters, right? If your DBA is like it's 200 milliseconds and you're like it's 0.3 microseconds and they're like, So it's a deeper conversation about what's going on there. So I thank you all for coming and I'll see you somewhere, probably at the bar tonight. All right.